Humans tend to spread rumors, often false, about each other from person to person to person. Routing protocols advertise accurate information from router to router to router. Let's take a look at the basics. Let me set the context. Feel free to skip ahead to the next chapter if you want to get going with it. I always follow the outline of the books. In this case, Volume 1, Part 6, Chapter 21. The current book has this green swoosh on it that says second edition, so that's where the Chapter 21 reference comes from. If you've got the older books, this content, you'd find it in Chapter 19 in the future. I'll try to update the description when the next edition comes out and point to the correct chapter, should the chapter number change. All right, so what's there? In that chapter, we've got three major headings that you see the titles of here. We're taking the first of those, and I've created a video. And that video has this outline on the right, and I've emphasized some different things in here. We'll talk about how to learn and advertise routes. I'll do a simple example to get us going, and then we'll focus on metrics for a bit. And I'll give some more attention to EIGRP than maybe I did in the books, and we'll also talk about OSPF metrics a little bit and get some big ideas pounded home. Then I'll compare and contrast exterior and interior routing protocols to give you that context, and then we'll wrap up. And in the wrap up, as always, I make these promises. For those of you with the books, I'll give you advice about what to read in the book section. For everyone, I'll give you a review exercise, and the something fun extra this time, OSPF is old, and so it's got some practical issues with the scaling of the metric called costs, so we'll talk through that for just a minute. All right, let's jump in and talk about routing protocols. Let's start out with a very basic description of routing and routing protocols. Then we'll get into some details about three specific routing protocols. We'll use this diagram throughout the video with R1, R2, and R3 with these WAN links, Ethernet WAN links between the routers and an Ethernet LAN on either side. And we'll focus on subnet 10130/24 and all three routers' routes to that subnet on the far right of the diagram. So in R1, its routing table entry is going to list that subnet ID and subnet mask as the destination because that defines the set of addresses that will match the route. And then from R1's perspective, it's forwarding instructions, the outgoing interface and the next hop router. So it was learned somehow, whether it was typed in as a static route or learned dynamically with a dynamic routing protocol. So R1 could forward that packet out this outgoing interface of gig 000 to next hop router 10.1.12.252, and it gets over to router R2. When R2 gets it, it matches a route that has, get this, the same subnet ID and mask in it, same destination set of addresses, but different forwarding instructions based on R2. R2's gig 000 interface presumably on the right, and next hop router 10.1.23.253 presumably router R3's address on that link. And then finally R3's route, same subnet. This one's a connected route going out its right-hand interface with no next hop router listed. Now this one for sure is not learned by a routing protocol. It's a connected route. It's that route to the subnet that sits out here connected to router R3. So let's talk about a generic, simple idea of how a routing protocol might advertise about this. Remember how R3 had a connected route? It didn't need a routing protocol to know a route to subnet 10.1.3.0. Well, it takes that information and then it's running a routing protocol and it's going to send routing protocol messages to router R2, advertising about the subnet ID and mask and some other routing protocol-y information, like a metric. In this case, it's showing a number of hops, all right? And it's basically saying, I'm no hops away, thinking router hops, numbers of routers. Router 3 is no hops away from subnet 3. So when router R2 learns this information in the message, it thinks my metric is one more than that. R2 is one hop away from subnet 3, and it adds a route to that subnet with the metric of 1. Then R2 sends a message over to router R1, lists hop count of 1. R1 says, let me add a little to that metric. Maybe my hop count is 2, right? R1's perspective, packets would flow through R2 and then R3 before they get to the far right subnet. So R1 adds a route with metric 2, and then it would try to send that information off to the next router if there was one out there. All right, so that's the general idea, but there are, of course, more specifics than that. And just to complete the story, let's say that R1 then wants to advertise about subnet 1 over here on the far left. Same idea. It has a connected route to that subnet on the left. It advertises that over to router R2. R2 adds a route to its routing table, advertises that over toward router R3. R3 adds a route to that subnet into its routing table. Let's talk a little more deeply now about routing protocols. Of course, routing protocols want to advertise about and learn about routes, but they also have metrics. And with metrics, they can choose the best route amongst many, and then they can re-choose the best routes when parts of the network fails or recover. To show you an example of that, consider the top part of this diagram, which repeats the one we just saw, but it adds a redundant path through router R4 so that R1 has a choice to make. Is it the top or the bottom path through the network that's the best route to reach subnet 10.130 now? Well, whatever routing protocol you're using, it would have a metric, a way to meter or measure how good each route is, and then R1 could choose the best route. For instance, some routing protocols, instead of using hop count, will use something that considers the speed of the links, like these. Here we have a 1 gigabit per second link. Is that good enough to make a routing protocol choose the top path over the bottom path, for instance? And it is in some cases and not in others. So you have to understand each routing protocol and understand the pros and cons of its metrics. So we'll do that here in the next few moments and get a small insight into how those metrics work. We'll start out with RIP because we just talked about RIP basically. That generic example used the RIP hop count metric. So when R3 is advertising about things, remember how it advertised and said, hey, I'm directly connected. And then eventually R1 learned it had a route to subnet 3, but it was 2 hops away. Its metric is hop counts, 1 and then 2 hops away. Whereas R2's route is 1 hop away. And R3's route, the metric, it says NA, connected routes don't even list a metric because, get this, the routing protocol has a concept of a metric, but the connected routes don't have a concept of metric. So there's no metric listed for the connected routes. Now let's look at the other 2 common interior routing protocols, starting with EIGRP. So that's from Cisco. It's Cisco proprietary. It's fairly popular. And if you were to run EIGRP, it would not use hop counts as a metric. Here's what it would do. By default, it would consider the link bandwidth and the delay. So each interface has a bandwidth setting and a delay setting. They're software settings. You can set them so they're meaningful compared to the actual physical link speed, but they're software settings. And get this, it's going to be based, the metric's going to be based on the minimum bandwidth in the route and the cumulative delay of all interfaces. So let me walk you through one to give you an idea. So we're back to this subnet 3 on the far right, and we see the bandwidth is 1,000 megabits, that is 1 gigabit per second. So when R3 advertises about subnet 3 with EIGRP, it says, hey, my minimum bandwidth between me and this subnet is 1 gig, and my total delay is 1 because the delay setting on that right-hand interface is 1. All right, so that message gets over router R2, and R2 thinks like this. Well, I learned a route to subnet 3. Let me add that route to my routing table, and I'm going to calculate a metric based on that minimum bandwidth of, 100 megabits. Now, didn't I just hear 1 gigabit in that incoming message? Yes. But what it does, it looks at that message, but says, hey, my interface has a 100 megabit per second bandwidth setting. I want to use the minimum of all links between R2 and the destination subnet. Well, that minimum is now 100 megabits. So it does this calculation based on the slowest link between R2 and this destination. But the delay calculation is the delay in the message plus some more delay for R2's outgoing interface. Here it says that interface's delay is 10, so it adds 10 more to get 11. Whew, isn't that fun? So it does a calculation. And if then you compare that to what happens here at R1, R1 receives this message that says minimum bandwidth 100 meg, total delay 11. Well, its link from R1 to R2 is a 1 gigabit per second link with a delay of 1. So its minimum bandwidth is still 100 meg. That is 1 gig, 100 meg, 1 gig. So the minimum is 100 meg, but the delay is a little more than it was with R2 because we added delay 1 for this interface off of R1. Now that's the first time you've seen this idea with EIGRP, so it's okay if you don't, digest all of that at once. Point is, it's using this metric based on the slowest link speed, slowest bandwidth in the route, plus the cumulative delay in the route. Now let's talk about OSPF. We've got our same topology diagram here, but what happens with OSPF is that each router creates a data structure for itself called a type 1 LSA. And it describes the router, its interfaces, its interface IP addresses, their OSPF costs, which is the metric. And each router creates a type 1 LSA for itself, and then it advertises its LSA to everybody else. All right, so it floods it, so everybody learns the type 1 LSAs of the other routers. Then on Ethernet links with 2 or more routers, one of the routers creates a type 2 LSA with data about the link, the subnet. So in this case, we've got one such link between R1 and R2 and another between R2 and R3. So some router creates a type 2 LSA for each of those, and those LSAs are flooded. Now the LSAs are just data in a data structure that's advertised with OSPF messages. But at the end of this, R1, R2, and all three know all of these LSAs. And in effect, they can create a mathematical model, a mapping of the entire topology with all OSPF-related information in them. Once they have the data, they will run an algorithm called the SPF algorithm, shortest path first algorithm, to calculate the best routes from its perspective. Open, shortest path first, is the name of the routing protocol. So for example, R3 creates its own type 1 LSA. It's got detailed info in it. It's got a router ID to identify itself as this particular router. And when R2 gets that, it doesn't calculate a route immediately. It adds that LSA to its database of LSAs called the link state database. And then it floods that LSA on to router R1. So eventually every router gets a copy and it stores it in its link state database for later processing by that SPF algorithm. Then if you flip it around and think about subnet 1 on the left, R1, or sorry, not subnet 1, but router R1. R1 creates an LSA for itself, a type 1 LSA, sends that to R2. R2 stores it in its LSDB, sends it on to R3. R3 stores it in its LSDB, but still no routes. So the second wave then is once the routers have information, they run this SPF algorithm to calculate routes. And part of what they have in those LSAs is a cost associated with each interface. So let's think about R1's route to subnet 3 on the far right for a moment. Turns out the way OSPF would calculate the cost for that route, there might be other alternatives, but as drawn here, there's just one. It'd be, get this, the sum of the outgoing interface costs. So in this case, from R1's perspective, it'd be this cost of 1 plus this cost of 10 plus this cost of 1 for a total of 12. So if this was the only available OSPF route from R1 to subnet 3, that's the route that would appear in R1's routing table with metric 12. And similarly, R2 would calculate, hey, cost 10 plus cost 1 in that route for a metric or cost of 11. And then R3's route to that same subnet, it's a connected route, so it would not have any cost associated with it. All right, so that's a simple case and a simple calculation with no redundancy, but what about this case with redundancy? Well, it would calculate the metric over the top path and over the bottom path, and it would choose the best path. Then, should anything change, it could choose, hey, that route is down, let me choose the other path. And this process of changing to choose a different route is called convergence. That's the generic word for it. So let's just say right now that the R1 routing table for subnet 3, it references an outgoing interface of gig 000 to next hop router 10.1.12.252, and we've added that information into the diagram. So this is telling us R1's route to subnet 3 is over the high road. All right. So the routing protocol converged, and R1 shows this top route over to subnet 3. Now I've added the cost values up at the top, say cost 10, and cost 1, and notice the metric is 21. 10 plus 1 gets us to 21. Now presumably that would be better than the cost over this bottom path, but let's just say, for instance, something in this chosen path fails, like we've got a failure on that WAN link where we got the big red splash that showed up. So OSPF would then calculate, oh, what's my alternate route that's available? And it would add this route with a different outgoing interface, different next hop router. This is the replacement route that shows up in router R1. Now its metric is 111. That's why we didn't pick it to begin with, because it had a worse metric than the one on the high road. This, of course, is the low road. And here we've got a cost 10, cost 100, cost 1. So 10 plus 100 is 110, plus 1 more is 111, and that's where we get the metric 1. How do you get a cost 100 and a cost 10 on the interfaces? Well, that can be configured directly. It can be derived from bandwidths. That's a topic for a later chapter. But that's an example of how OSPF convergence happens. To close, let's talk about some more terms and some big picture ideas. Over time, there were several routing protocols that were developed. Some were optimized for use within one organization and others for use between organizations. And it turns out there were several routing protocols with no one clear winner for inside a company, but there was one clear winner for the routing protocol to use between companies. And that winner is called Border Gateway Protocol. Now there's an archaic term called exterior routing protocol or exterior gateway protocol to refer to the idea of all the routing protocols to be used between organizations, and then BGP just won. Beat the competition. They've been the winner for, decades. All right. So the only remaining EGP is BGP. So what's the idea? So if you've got 3 ISPs and they want to exchange routes, their routing tables tend to be rather large, containing the routes for the entire internet. So they would exchange those routes using Border Gateway Protocol. Then between an ISP and its larger customers, they would use BGP. Smaller customers with less complex internet connectivity, say one link between themselves and the ISP, might use static routes instead. So there's no requirement that BGP be used. But if you've got 2 organizations and you're exchanging routes, more than likely you're using BGP. BGP can sometimes be used inside a company as well for different reasons. So it's not restricted to just be between companies, but think in terms of it's good for large scale uses like connections for sharing routes between 2 companies. Now, in contrast, the term interior routing protocol or interior gateway protocol, the word gateway was an old term for router, by the way. That meant the class of routing protocols that are optimized for use within one company. All right. And we've heard of 3 of those today: RIP, EIGRP, and OSPF. So let me just give you a few key points of comparison. Today, they all use multicast IP address to send their routing protocol messages so that they can send one message and have all the routers in the same subnet hear a copy of that. 2 of them are defined in RFCs, so they're standardized. But this middle one, EIGRP, is Cisco proprietary. So if you want to run EIGRP, you're running Cisco routers. Now, convergence, that process by which the routing protocol recognizes there's a failure or a link that comes back up and reconverging to the new best route. EIGRP and OSPF are fast. RIP is notoriously slow. All right, so that's one of the reasons why RIP is far less popular than OSPF and EIGRP. There's an underlying algorithm called distance vector with RIP and link state with OSPF. All right, those are the clearest terms. Now, EIGRP, people will argue whether it's a distance vector protocol or, as you see in the note, if it's an advanced distance vector protocol or a weird name called balanced hybrid. I don't care what you call it. Just know that it's not, if you think of RIP as distance vector, some of the internals, which we didn't talk about here, EIGRP is a little different. And then finally, it says, is it classless? That is, does it deal well with a feature called variable length subnet masks, and all three of them do. So you're prepared. All right, so that's a bit of comparison between the three routing protocols, and you'll hear more about some of these features as you march through your CCNA learning. So what about that book section? Well, you can skip it. This video is pretty comprehensive compared to the book section, so if you want to pick up some time, go for it. Then review activity, a terminology mind map. I've introduced a lot of new terms in this section, so do that as always. If the difference is you're not going to do it if you don't do it now, do it now. It's better for you if you'll wait a day or two and even schedule it. And your seed term this time is routing protocol, and just write down all the terms you can think of and organize them related to that term. Then last up, I promised you something fun as usual to think about. It's like, well, this is something you'll learn more about in a later chapter, but the default OSPF costs come from a formula, and the formula is based on an RFC or an interpretation of RFC that's, 30 years old. All right, so just for perspective, the OSPF RFCs predated, the original ones predated 100 megabit fast Ethernet. All right, so here's the thing. There's a setting called reference bandwidth in the routers, and if you have the default reference bandwidth setting, then the cost value on a 10 megabit link is 10, but the cost value by default then on 100, 1 gig, and 10 gig all tie at 1. So in other words, by default, OSPF sees how good these links are as equal, even though 100 meg, 1 gig, and 10 gig are far different in terms of bandwidth. So what you want is a way to scale up the metrics, so clearly OSPF will prefer the 10 gig link over the 1 gig link and prefer the 1 gig link over the 100 meg link. So you can configure this reference bandwidth. So if you look at these alternative reference bandwidths and the cost values that happen by default then at these speeds, you need to be somewhere over here with these reference bandwidths. This is very typical in production networks. So if I mention it in part to say, hey, if you're out there working while you're learning, and you can just ask your fellow engineers, hey, what do we have our OSPF reference bandwidth set to, and see what kind of reaction you get from your colleagues. All right, enjoy. Let me know if you do that. I'd be curious to see what happened. Thanks for hanging out to the very end. If you liked the video, please like. That's the #1 thing you can do for me to help me out with the channel. If you're new, thanks for coming and watching the video. Of course, subscribe. That helps. And it'll notify you, of course, when new videos come out, and click the bell so you get the appropriate level of notifications for your preferences. All right. Thanks for being here. Leave me a comment. Talk to you soon.